Hi, and welcome to this video on circular motion. Specifically, we're going to be talking about tangential speed calculations and centripetal acceleration calculations. One of the struggles when working with a circle is that you're not fundamentally moving in a straight line. What we need to be able to do is take our values about a circle or what we know about a circle and be able to calculate things like speed, velocity, acceleration. Some quick reminders for those who've forgotten. The circumference of a circle, or the distance around it, of a circle is 2 times pi times r. We use r in physics because it shows up in a lot more of our equations and because it's typically easier for us to find. Do remember that the radius is from the center to the edge of the circle. It is half of the diameter, which is the distance across the circle entirely. Things to keep in mind. A common calculation with traveling in a circle is calculating your speed. If you know, for instance, that you start here and you can go around the circle once and you come back here in, say, 45 seconds, if you know the radius, you can find your speed. For instance, this circle, let's say, has a radius of 10 meters. You go around the circle, it takes you 45 seconds. What's your speed? Well, speed is just distance divided by time. So in this case, 2 times pi times 10 over time 45. That'll give you your speed. Now if you're doing this at a constant speed, which is what we're going to assume for the time being, that'll mean that your speed is unchanging as you go around. And your tangential velocity at any given point will be equal to your speed. If we assume we're moving at a constant rate around the circle, which is what we're going to have to do for right now, we can go ahead and calculate this out. Find out what our speed is at any given point. In this case, our speed would be 1.40 meters per second after rounding. Now, if we assume that our speed is constant, which again we have to do, that means that here I'm going 1.40 meters per second, and here I'm going 1.40 meters per second, and here I'm going 1.40 meters per second, which means that my tangential velocity, or my velocity at any given moment, no matter which direction I'm heading, is also going to be this 1.40 meters per second. To state that a little more clearly, if you are moving at a constant speed around a circle, your speed is equal to the magnitude or value of your tangential velocity. So, if you can find if you know the radius and how fast it takes to go around, you can find the speed, and thus you can find the tangential velocity. The other common way you will see this stated is in revolutions per minute, or RPMs. There will also be rotations per second, or whatever. A revolution per minute is one trip around. So instead of, let's say you have a trip that if you're completing 7 revolutions per minute, you need to be able to convert this into meters per second, which involves unit conversion from way back when in chemistry. All it is one revolution is one trip around the circle. So one revolution is 2 times pi times r, meters. And 1 minute is 60 seconds. And this should, strictly speaking, be a lowercase r because capital R means something different. Once you have this translation, it's just plug into your calculator. 7 times 2 times pi times 10 over 60. So for this circle, 7 revolutions per minute would be 7.33 meters per second. Now, this is great. This is useful. We can calculate our speed, our velocity but this doesn't help us find our acceleration, at least not directly. In order to be able to find your acceleration, you need to be able to find your velocity, because via various derivations and calculations, we find that the acceleration centripetally equals your tangential velocity squared over r. That means if you are traveling at a constant velocity around a circle, your acceleration will always be pointing to the center circle, and will have a value of vt squared divided by your radius. That means that your centripetal force that's being provided in this direction will be your net force. And net force is ma. But since acceleration is, for a centripetal object, is fc, it'll be vt squared over r. So, for instance, if you have a pendulum, or if you have a person on a Ferris wheel, or you have a piece of rope that you're swinging in a circle at a constant speed, the acceleration provided by this must have a value equal to this, and the force being provided will be equal to this. What does this mean? How does this look? Well, go back a problem. We said that for a 10-meter circle, which 10-meter radius, 7 revolutions per minute is 7.33 meters per second. So, let's say you sitting right now in your chair, your mass, I'm going to estimate, is about 60 kilograms. My mass is closer to 100. You might be more, you might be less, but for quick, easy math, 60 kilograms. What is the force that would be required to make this transit? Well, we can find the acceleration using this equation here to get 5.37 meters per second squared. And there you have it, that your centripetal acceleration, your acceleration towards the center of the circle, is 5.37 meters per second, which means the force acting in the centripetal direction is 60 times that 5.37, which is 322.41 newtons. And we're done, right? Simple, easy peasy. We can find the centripetal force. There's just one small problem. The centripetal force is not a force in of itself. That is to say, the force between me and my pen, or the force between you and the earth, is never going to be defined as the centripetal force. It can act as a centripetal force, but it is not the same. What I'm saying in another way is that force gravity can act as a centripetal force, at which point we can use force gravity to make all these calculations. But the force that is causing you to rotate has to be provided by something. Going back to the rope and swinging, in this case, the tension of the string is my centripetal force. When you drive in a car going around a corner, the friction of the tires connected to the pavement is your centripetal force. A known force acts as a centripetal
force.
Let's take this a step farther. Take a look at pendulums. In the last video, we drew these free body diagrams and talked about the various forces on them. Let's take a little closer look at B, where all the forces are acting in a singular direction. We'll go through, use the centripetal acceleration equation, and use it to find how fast the pendulum is moving. So, we start with a free body diagram right here. And as we are wont to do with anything involving forces, the sum of all forces equals m times a. And in this case, we only have the y direction. Everything's acting up and down. So in this case, ft minus fg. Unlike previous units where I either stated they're standing still or gave you defined acceleration, in this point they're moving in a circle, so we can make some assumptions. First, some facts. In this case, the pendulum has a mass of 0.50 kilograms, and the string has a radius of 1 meter. What I want to know is how fast is it moving at point B? Well, how do we do this? How does this look? Because it's moving in a circle, we can say mvt squared over r, putting in our value or equation for a centripetal equals our force tension, and we can say force gravity is m times g. Now, you'll notice a small problem. We have masses, we have the radius, we're looking for the velocity, we do not know the force tension. So if we wanted to do this problem, we need to know the force tension. We need to get it somehow. We could use one of those spring scales and hang the pendulum from it, have it swing back and forth. As we did, we'd see that the force would vary. But at the point B, at the lowest point, we find that the force is 6 newtons at point B. Now we can go forth and solve it. I'm going to rearrange and solve symbolically. Vt over r equals ft minus mg over m. Multiply both sides by r. Vt squared equals r ft minus mg over m. Vt equals the square root of r ft over mg over m. So just plug in your numbers and you get Vt. And I get that it's moving at 4.69 meters per second at the bottom. And there we go. Easy peasy kind of idea. All it involves is using this equation to do it. But life is rarely that simple, rarely that easy. What we want to be able to do is also be able to calculate unknown forces or use known forces to go through and solve these problems. The setup will almost inevitably be the same. Draw your free body diagram, figure out where your centripetal acceleration is, and set up the equation such that your sum of all forces equals ma, and then your a will be your centripetal acceleration, which is your tangential velocity squared.
Over r.
From there, it's just like solving any other force problem. Let's set up one more, and you'll be able to try it on your own. So despite common knowledge, which is often wrong, the way tires work is by rotating and using the static frictional force to grip the road. When you start skidding or sliding, that's when you switch from static to kinetic. So on a perfectly good driving day, the frictional force of your car gripping the road is the mu static. With that said, on a typical day, you have a mu static max gripping the road of 0.9. Now, if it's rainy or your tires are worn out, this value decreases. But with that in mind, with that thought of, you're driving your sedan, your car, which has a mass of approximately 1,000 kilograms. You're going to go around the corner. You're going to take effectively as if it's a circle with a radius of 8 meters. What's the fastest you can take this corner?
Also, do that calculation for both rubber and asphalt and rubber and concrete.
Go ahead, give it a try. If you're stuck, look back at the previous video and go through how we drew the free body diagram for a car going around the corner. Okay, here we go, starting from the top. I started by drawing the free body diagram for a car from the back, like we did in the previous video here. I then went through and wrote my sum of all forces equation for y and for x. I just suck at labeling x's. There we go. From there, I went through and solved both my equations. Sum of all forces y, well, it's not moving up and down, it's moving around the circle, which is in the x direction as drawn here. So my acceleration in the y direction is 0 because it's constantly on flat ground. At which point my sum of all forces x equals ma equals force friction. Because it's moving in a circle, my x direction is a centripetal acceleration, I can put vt squared equal over r. Again, for my a, I substitute mu times Fn in. I noticed I had mass on both sides, so I divided it out once I plugged in my expression for Fn into this equation. And then I brought it over here to simplify down and solved and got this expression. This would be your maximum value. And so you're going to be at your maximum velocity when you have your maximum mu value. So 0.9 for rubber and asphalt, 1.0 for rubber and concrete, which tells me that I can go around this corner at 8.4 meters per second if I'm in a car with rubber and asphalt, or 8.85 if I'm on a concrete ground. Now, this also demonstrates a lot of other things. We'll notice that, like from our expression, that the velocity will go down if my mu goes down. So if, for instance, it's raining and the grip on the pavement decreases, the speed you can take that corner at decreases. If you have a tighter circle, a sharper corner, the speed you can do it at decreases. But if you have a larger circle, say like a roundabout or a clover leaf, as the radius goes up, so is the speed you can take that at. It's part of the reason why clover leaves are so large. But the idea, the expression, the calculations are all here. Anyways, there you have it. Thanks for watching. Have a good one.